Today, we're delving into Unit 3.5 of the first half of General Chemistry, which covers formulas and equations. If you find value in this video, please like it and let people know about the channel because it really does help spread the knowledge. As discussed in Unit 2, the molecular formula of a substance provides information about the proportionate quantity of atoms for each element present in the substance. For example, in H2O, there are 2 hydrogen atoms to 1 oxygen atom, and as stated in the previous video, there are 2 moles of hydrogen to 1 mole of oxygen in 1 mole of water. In the case of water, H2O is the molecular formula as well as the empirical formula. Empirical formulas represent the simplest ratio of elements present in a compound and are commonly used for compounds with complex structures or when the exact arrangement of atoms is unknown. It does not provide the actual number of atoms but rather shows the relative proportions. For example, the empirical formula of glucose is CH2O, indicating that for every carbon atom, C, there are 2 hydrogen atoms, H, and 1 oxygen atom, O, in the compound. On the other hand, a molecular formula gives the actual number of atoms of each element in a molecule. It provides a more precise representation of the compound's composition. Using the example of glucose, its molecular formula is C6H12O6, indicating that a glucose molecule consists of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. This is the reason we focus on molecular formulas. They are more precise and give more useful information. One of the most fundamental equations you'll need to solve for as a chemist is how to calculate the amount of reactants and/or products that are needed and/or produced in a given chemical reaction. Let's say you are a medicinal chemist that just got an order from your boss for 5 kilograms of lidocaine, a local anesthetic commonly used at dentists. You're a perfect chemist and have made it before, so you know one of the syntheses, which is C4H11N plus CH2O plus C9H9N, going to C14H22N2O, but you need to know how many grams of the starting materials you'll need to buy. So, where do you start? You start with what you know, which is you need to make 5 kilograms of lidocaine and convert that to moles. In these types of equations, it is often the best place to start by converting everything to moles. To do this, you multiply the atoms in the molecular formula by their atomic mass units, like we learned previously. There are 14 carbons, which is 14 times 12.011 AMU plus 22 hydrogens, which is 22 times 1.008 AMU plus 2, nitrogens, which is 14.007 AMU plus 1 oxygen, which is 15.999 IMU, coming out to 234.343 grams per mole, the molecular weight of lidocaine. Once you know the molecular weight, you can calculate how many moles you'll need. Remember, the molecular weight is in grams, so you have to convert kilograms to it, which is 1,000 grams per 1 kilogram, and then divide by the molecular weight to get 21.336 moles of lidocaine. Looking at the synthesis again, you see that it is a 1-to-1-to-1 reactants going to one product, since there are no coefficients in the formula. C4H11N plus CH2O plus C9H9N going to C14H22N2O. This means that you'll need 21.336 moles of each starting material. Then you convert these moles to grams using the molecular weights. By now you know how to calculate molecular weight, so I won't show you that again. I'll give it for each starting material. 73.14 grams per mole in C4H11N, 30.03 grams per mole in CH2O, and 131.18 grams per mole in C9H9N. Once you have the molecular weights, determining the grams is just multiplying the moles by the molecular weights as such. 21.336 moles of C4H11N times 73.14 grams of C4H11N equals 160.5 grams of C4H11N. 21.36 moles of CH2O times 30.03 grams of CH2O equals 640.7 grams of CH2O. 21.336 moles of C9H9N times 131.18 grams of C9H9N equals 2798.9 grams of C9H9N. It is important to keep in mind that this is assuming you are a perfect chemist and 100% of the molecules react to form the product. This is seldom the case, so in the next unit we'll go over some of the imperfections in chemical synthesis. Based on what you learned, think about the following question. Provide the balanced equation of the combustion of hydrogen and oxygen to form water, and calculate the grams of hydrogen and oxygen needed to produce 1 gallon of water.
Thank you so much for spending your valuable time learning and bettering yourself. If you like the video and want to learn more, donate, or get tutoring, please check out my website, nocollegeneeded.org. You can use the code NCN for 20% off tutoring and any supplemental material.